In this video, we are going to study about one of the important formula in graph theory that is given by Euler, and it gives the number of regions for any connected graph. Number of regions plus number of vertices minus the number of edges is always equal to 2. In other words, a connected planar graph with n vertices and e edges has e minus n plus 2 regions. Or I can even write, if f is the number of regions, then f plus n minus e is always equal to 2, which is known as Euler's formula in graph theory. So let us prove this formula. I'm taking simple connected graph because, see, if I have a self loop or a parallel edge in my graph, then number of edges just increased by 1, right? So the self loops always increase number of regions by 1, and even the parallel edges. So simultaneously number of edges are also increased. So I'm avoiding that situation. So I'm proving for the simple graph. And one more, it is sufficient if I prove for the graphs which do not have a pendant vertex. In the sense, I'm removing those edges which are not the boundaries for any regions. If I have a pendant vertex, then number of vertex is also increased by 1 and number of edges also increased by 1. Okay, so e minus n value is unaltered. So I'm removing those situations, these three situations, that is simple graph. I'm proving only for the simple graph which has no self loop, no parallel edges and no pendant vertices. So it is sufficient to prove this theorem for the simple graph without self loop, no parallel edges and no pendant vertices. Okay. I know that any simple graph can have a plane representation such that each edge is a straight line. Okay, then I can say each region can be considered as a polygon, including the unbounded region. Each region I am considering it as a polygon. Now let us take, let f is the number of faces or number of regions in the graph. Number of faces or number of regions. F denotes number of faces or number of regions, and let ki, I'm writing ki is the number of I-sided region. Number of I-sided region. Like if I have K3 gives me number of triangles. Triangles, 3-sided, no, so it gives me number of triangles. K4, it gives me number of quadrilaterals, like that. Okay, so Ki denotes number of I-sided regions. Since I know that every edge is a boundary for exactly 2 regions, every edge in my graph, suppose I have something like this in my graph, then each edge is a boundary for 2 regions. I know that. Therefore, I can write 3k3 plus 4k4 plus 5k5 dash 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 rkr is nothing but 2 into number of edges. Why I am starting from 3k3? Because, see, I am avoiding the situations region which has only 2 edges. That means it has got self loop or a parallel edges. I am leaving that. Okay. So first polygon I am getting is the minimum one, that is with the 3-sided. Okay. And 3 into k3 K3 is number of triangles, K4 is number of quadrilaterals, like that. Okay, R, let me take R is the number of edges of a largest polygon. Okay, now 3K3 plus 4K4 plus 5K5, like that. RKR is nothing but 2 into E. 2 into E because every edge is boundary for exactly 2 regions. So let me call this as equation 1. Equation 1. Now I also know that each polygon is a region, and it creates a region. Adding these polygons, it will create one more big region, and that is nothing but F when I consider its total number of regions. Okay, it's nothing but sum of triangles, sum of quadrilaterals. So there are R such polygons, R sided polygons. So K3 plus K4 dash 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 KR gives me total number of regions in my graph, and I'm calling this as equation 2. Now I know that each vertex is surrounded by angle 360. This angle is distributed among the different polygons. Okay, now there are n vertices in my graph. So the sum of all the angles, subtended at each vertex in the polygon is 2n pi. See, if I consider one vertex, then total angle at this vertex is 2 pi. There are n such vertex, so total angle, sum of all the angles in this graph at each vertex I am considering, that is n into 2 pi. One vertex 2 pi, there are n such vertex, so sum of all the angles at each vertex in the polygonal net is 2n pi. Okay, now this you should remember. Now I can also calculate sum of angles in another way. Okay, so I'm recalling this sum of all the angles as sum of interior. This is an example. Okay, sum of all interior angles plus sum of all exterior angles. Okay, so total angle I can even write it as sum of all interior angles plus sum of all exterior angles. Now we know that for a polygon, if polygon is p-sided polygon, for p-sided polygon, total interior angle or sum of all interior angle is total interior angle is nothing but pi into p minus 2. Okay, and total exterior angle is, or sum of all exterior angles is, pi into p plus 2. Now I am using these two formulas to calculate the total sum. Okay, it's sum of interior angle plus sum of exterior angle. See, now what happens is, when I consider such graphs, now total interior angle means it gives me sum of this, sum of all these interior angles. Okay, no problem with the interior. But when I consider sum of exterior angle, now see, for this polygon, exterior angle is this. Okay, but it is included in interior angle of this, right? So I want interior angle of all this and the exterior angle of this whole graph, means whole this polygon only. Only for this polygon I want the exterior angle. Okay, why? Because interior angle of some graph, some polygon is an exterior angle for the another polygon. So I want sum of the interior angles of all these finite regions and the exterior angle for only this unbounded region. Okay, so I'm computing this total angle as sum of all interior angles of f minus 1 regions plus sum of the exterior angle of one unbounded, one infinite region. So I'm writing total angle as, or sum of angles as, sum of all angles, I'm writing it as interior angles of f minus 1 finite region plus exterior angle of polygon representing infinite region. So that will be equal to pi into, for K3 it is for a triangle it is 3-sided, no? So interior angle is 3 minus 2 into K3. Similarly for K4 it is 4 minus 2 K4, like that, plus for R-sided polygon it is R minus 2 into KR, plus I'm taking 4 pi as an exterior angle for the infinite region. Why? Because see, total interior angle is pi into p minus 2, okay, and exterior is p plus 2. I have to remove all these interior angles from this total exterior angle. Why? Because exterior angle for one polygon is an interior angle for the other. So I have to remove total interior angles from the exterior angle. So that is p minus 2, which gives me 4 pi. So I want only the exterior angle for this infinite region. Okay, this is an example I am considering. For this I want the exterior angle, that comes out to be 4 pi. So I'll rewrite this expression now. This can be written as 3 pi K3 minus 2 pi K3, like that, 4 pi K4 minus 2 pi K4 dash 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 pi R KR minus 2 pi KR plus 4 pi. This can be written as, if I take only the first terms every time, so if I take pi outside, then I am going to get 3k3 plus 4k4, like that, rkr. Okay, and from these negative terms, if I take out 2 pi outside, then I am going to get k3 plus k4 dash 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 plus kr plus the last term, that is exterior angle for the infinite region, that is 4 pi. Now this is nothing but pi into this. I have used 3k3 plus 4k4 dash dash rkr is nothing but 2e by the expression number 1 and minus 2 pi into k3 plus k4 dash dash dash, that gives me total number of regions, that is f plus 4 pi. So I can rewrite this expression as pi into 2e minus 2f plus 4 pi. Okay, now this is the total angle. I have calculated by using the total interior angles plus total exterior angle. So this must be equal to total angle subtended at each vertex in the graph, that is 2n pi. So this, I am calling this expression as expression 4. So equating expression 3 and 4, or 3 to 4 I can write. It's nothing but 2n pi equal to pi into 2e minus 2f plus 4 pi, which is nothing but n equal to e minus f plus 2, or if I write it like this, then f equal to e minus n plus 2, or you can write it as f plus n minus e equal to 2. Hence the proof. Now the corollary to this theorem, it states if any simple connected planar graph with f regions, m vertices and e edges, of course number of edges is greater than 2, then following these inequalities must hold. See, it's because if I have a planar graph, then each region is bounded by at least 3 edges, at least, okay. Each region is bounded by at least 3 edges, and each edge contributes, each edge belongs to exactly 2 regions. Okay, therefore I can write 2e is greater than or equal to 3f. That is same as writing e greater than or equal to 3 by 2f. Say suppose if each region is a triangle, then there must be 3f by 2 edges. If the graph has other regions, then the number of regions will be more, that is e greater than or equal to 3f by 2. For a planar graph, we have the Euler's formula, that is f is equal to e minus n plus 2. Now substitute this e greater than or equal to 3f by 2. We are getting 2e by 3 greater than or equal to f. F is nothing but e minus n plus 2. Okay, I am substituting this. Now 2e is greater than or equal to 3e minus 3n plus 6, that is 3n minus 6 is greater than or equal to e. So these two holds good. This inequality, that is e less than or equal to 3n minus 6, it is always useful for finding out the graph is planar or not. Okay, suppose if I take k phi, okay, k phi, I have got number of vertices as 5 and number of edges as 10. Now when I consider 3n minus 6, which is equal to 9, which is less than e. Okay, so it violates the inequality, therefore I can say it is non-planar. Remember one thing, this inequality is a necessary condition, but it is not a sufficient condition, because when I consider k3 3, In K33, number of vertices is 6 and number of edges is equal to 9. So that 3n minus 6 is 12. But still the graph is non-planar. Therefore, this inequality is a necessary condition, but it is not sufficient. In K33, there are no triangles. Okay, therefore, what happens is each region has got 4 sides. Therefore, graph should have minimum 4f by 2 edges. I got the point. Each region, since there are no triangles in K33, I have got each region which is of minimum 4 sides. So the number of edges which I am considering is greater than or equal to 4f. Therefore, E is greater than or equal to 2f. Now if I apply the Euler's formula for this, then I am getting E greater than or equal to 2 into f. F is E minus n plus 2. Therefore, I am getting E minus 2E greater than or equal to minus 2n plus 4. That is same as writing E less than or equal to 2n minus 4. So the formula is changed when you consider K33. So I can't use this. Okay, therefore and hence I know that for K33 E is 9 and n is 6. So if I use this formula 2n minus 4, then 9 is less than or equal to 8, which is not true. Therefore, K33 is non-planar. Next is homeographic graphs. Two graphs are said to be homeographic if one graph can be obtained from the other by the creation of edges in series or by the merger of edges in series. Creation of edges in series means I am inserting a vertex of degree 2 in series. Okay, merger means I am just fusing, how you do like that. I am merging the vertices. So I will give you an example. Suppose this is my graph. So now these are the vertices. From this graph I am obtaining one more graph like this. These are common. I am just taking like this. And one more, if I put one more vertex over here or here, then I'll add a vertex of degree 2. Now these three graphs are the homeographic graphs. So we have got the necessary and sufficient condition for a graph to be planar. That is, if my graph contains K5, K33 or any such homeographic graphs, then I can say that graph is non-planar. I repeat, a necessary and sufficient condition for a graph to be planar is it should not contain either of two Kuratowski's graphs or any graph homeographic to either of them. Okay, so the theorem, it says a necessary and sufficient condition for a graph G to be planar is that G does not contain either of two graphs K5, K33 or any graph homeographic to either of them.